Hi, everyone. Thank you for being here. My name is Ethan Ayari. I'm a third-year physics graduate student at the University of Colorado Boulder, working under Dr. Mihai Harani. Before we get started, I'd like to thank the people funding this work, Impact, LASP, CU Boulder, JPL/Caltech, and FU Berlin. So what we're talking about today is modeling the impact ionization time of flight mass spectra measurements of interplanetary and interstellar dust particles. And we're going to get into exactly what that means. This talk is going to outline what it means to model these measurements, the parameter space for our modeling, including instrumental effects that we see from missions, using the dust accelerator that we have available to ourselves at Impact/LASP, and then some applications and future research with this modeling. So II-TOF-MS is impact ionization time of flight mass spectrometry. It's a method to provide in situ composition measurements of cosmic dust particles. These are really informative in situ measurements, but we do not have a ton of past mission data. So what this calls a need for is numerical reference spectra, which we're working on now. So I show an example here on the right. On the top, we see the cosmic dust analyzer that flew aboard the Cassini mission. And then below it, you see the same mineral, but on a newer prototype. So you can see how much mass resolution has improved since the days of Cassini and our ability to distinguish individual isotopes. So the way that these instruments work is that we have an incoming dust particle. It impacts a biased target that's at a few kilovolts. This generates an impact plasma, which is focused onto a detector by a series of biased electrodes. I think it's worth mentioning that multiple of these modern instruments are flying on upcoming missions. So we have the Interstellar Dust Experiment aboard the upcoming IMAP mission. We have the Surface Dust Analyzer on the Europa Clipper mission, and a similar instrument is flying on JAXA's Destiny Plus mission. When the dust particle is detected, we generate three types of signals. You can see at the top there's the target signal. Below it is the ion grid signal. These both provide an estimate for the impact charge of the dust particle. And then below it is the time of flight mass spectrums, where we can determine the composition of the particle, since the flight time from the target to the detector is proportional to the mass to charge ratio of the ion. So the way that we're generating numerical data and trying to model these measurements for future missions is that we start off with the raw composition, so the stoichiometric ratios of our intended sample. From there, we generate realistic noise. This is done by looking at the power spectrum from existing mission and accelerator data and basically applying it randomly throughout, giving us a tunable SNR. And then finally, we look at trends with speed in our measurements and try to replicate them. What I'm showing on the right here is a numerical spectra on the left that was created to model the laboratory spectra on the right. This is a 50-50 phyolite olivine mixture. And as you can see below, I project the magnesium isotopes, and these ratios are reproduced pretty well by the numerical spectra. We chose to focus on three mineral families due to their significance and abundance in the interplanetary dust particles. These would be the olivines, the pyroxenes, and feldspars. When we make a composition measurement for any of these three mineral families, what we're trying to do is place them on which are called ternary diagrams. So in the case of olivine, we can determine how much iron versus magnesium there is, as well as calcium inclusions. With olivine, the two green bands here represent fully soluble series. So we can have any composition between the two magnesium iron end members. This measurement actually has a velocity dependence, so the abundance of ions that you measure from the impact plasma is dependent on the impact velocity of the dust particle. A paper by Caterina Figa in 2014 established this velocity dependence for silicates. And the way that she did that is that she provided these mass line appearance probabilities. So on the x-axis is the impact velocity in kilometers per second, and then the mass line appearance probability is given on the y-axis. The way that we're handling this in the numerical modeling is that we have two random numbers. One random number will determine if a mass line shows up, and that's one that's compared to these probability curves. And then another one to reflect instrumental scatter determines the total line area of the corresponding EMG, so the mass line. This is the result of that. So I'm showing 3 albite spectra here at 5, 10, and 15 kilometers per second, decreasing as you go down. I think it's worth noting that the oxygen line doesn't peak out above the noise until about 15 kilometers per second, and you can see how the spectra changes with velocity. So generating the instrumental scatter that we see, we're able to do this for any mixture between the 3 mineral families. I chose to do an enstatite ferrocylite mixture. You can see what it looks like for different levels of scatter seen by the instrument. These plots are kind of how we try to identify composition. We plot elemental ratio versus elemental ratio on both axes, and we basically want to look for clustering. And if we see a really tight clustering here, as indicated by the topographic lines, then we can safely say that that's the composition of our dust particle. So in order to improve this modeling, we've been doing a lot of accelerator experiments at Impact/LASP. I'm showing you my favorite spectra that we took this year. It's a 15 kilometer per second, 79 nanometer olivine dust particle. And as you can see, the contamination levels are fairly low, as well as the noise. And this hyperdust instrument that we've been working with has the really convenient quality that all of the mass lines are roughly 20 nanoseconds in width. And it's far exceeding past instruments because we're getting a mass resolution of about 150 at 54 AMU. So things are looking really clear, and we're able to distinguish clearly between the magnesium and silicon isotopes, as you see here. So what we did with this San Carlos olivine sample is we plotted this elemental ratio versus elemental ratio plot, which I'm showing here. And you can see this really tight clustering in the top left. This allowed us to place it on the ternary diagram. I indicate that with the red triangle in the bottom left. And so the idea is that for any detection that we have, we can trace back the composition and map it to the ternary diagram, providing a really useful in situ composition measurement of dust. It's also worth mentioning that because of this velocity dependence, we try to look at most of our impacts at the accelerator at 19 to 25 kilometers per second. Any sort of ionization effects are pretty much negligible at that point, and you're measuring the entirety of the dust particle.
2 minutes.
Thank you. So, this is certainly still a work in progress. On the right, you can see my attempt at synthetic reproduction of the lab experiments. Right now, we're trying to study this sort of oblique scatter that we see in the lab experiments, where you can see some points kind of almost lying on a decreasing linear slope. So we're investigating those individual spectra, or just seeing if it's a normal chemical spread that we're measuring. So the key takeaways of this is that we are generating numerical reference spectra for olivine, pyroxene, and feldspar. These will be useful for upcoming missions that will measure dust particles of these 3 mineral families. We're continuing to incorporate additional accelerator experiments into this work. We have many scheduled for the rest of the year. And then finally, as we start using some more modern statistical tools, such as machine learning and the identification process of these spectra, I think these reference spectra would make for great training data for anybody trying to train a convolutional neural network, for example. Thank you very much.
Very good. Thank you, Ethan. Any questions online or in the room?
Hey there, Micah Scheibel, Georgia Tech. Do you have a feeling for the minimum abundance of especially the isotopic compositions that you can find?
So that would be like within the chemical formula, what's the smallest thing that?
Well,
we can-
so if you have, you know, 2 or 3 silicon isotopes, are you able to see silicon 30?
Yes, yeah,
So if you had 1% of silicon in your sample, would you still be able to see silicon 30?
I see now. It's really dependent on noise levels. Unfortunately, at the accelerator, we kind of have a lot of different, machines running, so our noise levels will vary. I have seen something as low as 3% abundance. That wasn't silicon, that was just a really small iron peak, but
Thank
yeah.